Alright, so in this lesson we're going to start talking about Kepler's laws, which is a set of three rules that we use to talk about planetary motion. These are developed by a gentleman by the name of Johannes Kepler in the early 1600s, and basically what this does is it solves a few problems dealing with the motion of planets and how the motion of planets differs from the motion of other objects in our sky. So to kind of explain, first of all, what the problem is, if we look at planets, is that it was fairly clear early on to observers who looked up at the sky that the planets were something a little bit different or a little bit odd. The main reason for it is they obviously don't look like the moon and the sun, which are very prominent in our sky. They're smaller, they almost look like stars when you look at them. But unlike stars, when you look at them, stars tend to have this twinkly look to them, mainly because of the distance that light has to travel from the star to the Earth. Planets don't have that twinkly look. They look like a solid color. If you've ever seen something like the planet Venus, which is very prominent in the sky in terms of planets, or the planet Mars, two that are very distinct colors. The other thing that makes planets odd is they don't behave like stars, the moon, or the sun. The moon and the sun obviously look like they move around the Earth in a circle. They always rise in the east and set in the west. If you look at stars, you notice they also always rise in the east and set in the west. The other thing that's cool about stars is, depending upon what time of year you're in, you see different stars at different times. So there's kind of two different cycles with stars. You have the rising and setting of the stars, but you also have a different set of stars that regularly repeats itself over a yearly basis. So what most early observers kind of did with the stars, moon, and the sun was they created a system of the universe where the Earth is at the center, the moon is kind of the next level up, the sun, the stars, but the planets don't really fit very well in that system. Depending upon what type of mythology or religion or stories went along with the planets may have very different, there may be very different explanations for the planets depending upon where you look in the world. However, this idea that the Earth's the center of the universe and that other things orbit around the Earth is a pretty common theme if you go and look at different religious ideas and different philosophies kind of in the ancient world. So where this model starts to change, at least in the Western world, is with a guy by the name of Nicholas Copernicus. And so what Copernicus basically did is he said, what if we have the sun be the center of the universe and the planets, including the Earth, orbit around the sun? As you might have guessed, if you're coming from a system of belief where the Earth is the center of the universe, and if you think about where Nicholas Copernicus is from, he's from Italy in the 1500s. So the Earth is the center of the universe because the Earth is the center of God's creation. If we think about what's going on in Italy at this time, it's really the Catholic Church that's in charge of that country. So this would be a very bold and out there idea. What this idea does is it solves the problem of why do the planets behave like they do, because if you put the sun at the center and you make the planets do circular orbits around the sun, it actually resolves the motion that you see with planets. This weird, what we call retrograde motion that looks like a planet goes this way, then suddenly turns around and goes the other way. So Copernicus proposes this idea in a book he writes that's actually published the day after his death. It's actually intentional that's published the day after his death because he doesn't want to be, punished for his writings or his heresy that the Earth is not the center of the universe. So the next person that kind of takes up the mantle of trying to describe how this all works is a guy by the name of Tycho Brahe. And Brahe is from Denmark. He has probably one of the best observatories in the world in the late 1500s. He is related to the monarchy in Denmark, so he's actually has a spot in line to the throne. He is an aristocrat, and he's basically interested in looking at planets. And so he's very good at using his telescopes in his observatory to get very good measurements of where the planets are at different times of the year. What he is not very good at is actually crunching the numbers and showing what is the mathematical relationship or the geometric function that makes all of this work. So his system that he's proposing is, sure, all the other planets orbit around the sun because that makes their orbits work well, according to Copernicus, but the Earth is still the center of the universe and the sun orbits around the Earth. As you might guess, this is a fairly complicated system of the universe, or a fairly complicated system of our solar system, but it would mathematically work out if you decided to set it up this way. I actually had my graduate school advisor said there's nothing inherently wrong with thinking of the universe or the solar system this way, other than the fact that it's harder to describe the motion of planets with respect to the Earth, or with respect to a fixed frame, if you're saying that the Earth is the center and everything moves around the Earth. So the guy who's helping crunch the numbers for Tycho Brahe is a guy by the name of Johannes Kepler, which is the guy for whom Kepler's laws is named after. So what happens with Tycho Brahe is that he's getting ready to start to publish his results. He's got Kepler working for him. Kepler's worked for him for maybe about a decade at this point. And he suddenly becomes ill and, well, dies. There's a number of different stories behind how he becomes ill. One of them deals with the fact that he was at this big party with other aristocrats. Back in that time period in his culture, it was actually considered rude or impolite to excuse yourself from a party to use the restroom. And so one of the stories is that he basically gained a bladder infection by not excusing himself and died from that. Another story is that he was poisoned. And the two most likely candidates for that are Johannes Kepler, the guy who's going to benefit from Tycho Brahe's immediate death because he's going to get all of his data, or one of Brahe's cousins, who first of all didn't really like Brahe, and second of all, it would move him up the order of line to the throne. However, Brahe died. He died. And Johannes Kepler gets all this data, and Johannes Kepler goes very quickly about his work, and he comes up with 3 rules for planetary motion. The one which I call the law of orbits. All planets move in elliptical orbits with the sun at one of the foci, This essentially confirms the Copernican model. The second is the line connecting the planet and the sun will sweep out equal areas over equal intervals of time. Another way to say this is that the change in area as you're looking at the area of this orbit is constant. And the third one is the square of period is proportional to the cube of the semi-major axis, the law of periods. Now, we've seen that before when we use centripetal force and Newton's law of gravity, and there's no surprise or no coincidence that we've seen that before. How Newton came up with Newton's law of gravity, he used Kepler's third law as a basis for what should this equation look like, and he verified if gravity is the force, here is what this force has to be like. So let's look at what these mean. So the first one, the law of orbits. So the thing to remember about an ellipse is that an ellipse is kind of like a flat, elongated circle. Ellipses have what's called eccentricity. An ellipse has what are called foci, 2 places here. How those places are defined is if you draw a line from this focus out to here, and then back to that focus, and add those 2 distances up. Anywhere along the ellipse, the sum of those 2 distances remains constant. So what eccentricity really does is it's a measure of how far away from the center is either of the 2 foci. The larger eccentricity gets, the further this gets away from the center, and eccentricity usually is defined as some number between 0 and 1 for an ellipse. So you have the minor axis, which goes the short way across the ellipse, the major axis, which goes the long way across the ellipse, and we talked about the semi-major axis, which is really half this distance, so this distance here. So we use the symbol A to talk about the semi-major axis, or that distance, so the major axis has a value of 2a in terms of length. Now there are 2 points that are interesting when we talk about in orbit. One is what we call the perihelion or perigee. This is where the planet is closest to the sun, and we can actually calculate that distance by using the eccentricity in the semi-major axis. The second point is the aphelion or apogee, And we can calculate that, again, by using the eccentricity in the semi-major axis. And those distances are basically a measure of how far you are away from the sun. Now we use perihelion and aphelion to talk about the sun and planets. Helion coming from Helios, the sun. We'd use perigee and apogee to just talk about a general orbit, say a satellite moving around the Earth, if it was in an elliptical orbit. Now it's true about the perihelion, you should be moving the fastest in your orbit here, and the aphelion, you should be moving the slowest. So let's look at this law of areas and see what this means. So here I've gotten an area that's swept out in a certain unit of time, and we can actually measure that area by taking half base times height squared. So half the base looks like it's the radius from here to here. The height looks like it's just whatever this arc length is, r times theta. So really it's 1/2 r squared theta. Now if we actually are changing that area, if we look at this change in area, if we looked at this and the next unit, r isn't going to change all that much, but delta theta is going to change quite a bit. If we're looking at this as a time rate of change, we'd write it this way. And if we're saying, what if delta t becomes really small, we really have a derivative. dA over dt is equal to 1/2 r squared d theta over dt. Well, d theta over dt is the same thing as omega. Now, if you have an r and an omega in here, well, those look like they might be related to momentums in some way, or angular momentums. So let's take a look at angular momentum for a second. And so what angular momentum really looks like is it's r cross p, or radius and momentum, the cross product between those two. And the way we would generally calculate that is r times the perpendicular component of p. Well, the perpendicular component of b would be mass times the perpendicular component of velocity, which would be the same thing as r omega would be the perpendicular component of velocity. So if we kind of work this out, we get an r squared omega in there. And so we can actually solve this out for r squared omega and substitute in that dA dt equals the angular momentum of the planet divided by twice the mass of the planet. This essentially says that angular momentum is conserved in orbits. That's actually a really helpful thing to have because it gives us a way to predict speeds at different points in the orbit that I can use angular momentum as a way to predict speed. The last one, the law of the periods, basically how he came up with this was he looked at the well-known planets of the universe. Here I've picked the 8 planets that we know of and Pluto and graphed their period squared versus their semi-major axis cubed, and what you get is a beautiful straight line. In fact, so straight that the correlation of fit is 1. We could actually find other objects, asteroids, other minor planets, and plot them out, and you see that they also fit on this nice straight line. We could pull this slope out and actually find, if we really wanted to, the mass of the sun too. So this is actually a pretty cool thing to do, and it's a pretty interesting thought exercise. And the data actually works out very, very, very well when you do this. So let's look at a quick problem dealing with some things with an elliptical orbit. And I picked Comet Halley, or Halley's Comet, and it orbits the sun with a period of 76 years. This happens to be one of the more well-known comets that we know 76 years because, well, we've seen it so many times in history, and it's actually one of the ones that prove that comets are in orbit around the sun. So it reaches perihelion distance of 8.9 times 10 to the 10th meters, which is the distance between Venus and Mercury in 1986. We want to know what's the comet's aphelion distance and its eccentricity. So I'm actually going to calculate the eccentricity first. Here are the things that we know. Here are some equations that we have that we could use. From period, I could actually get the semi-major axis. If I solve this out for the semi-major axis, looks like divide everything by 2 pi squared, multiply everything by gm, and then cube root, you get 2.68 times 10 to the 12th. If I know 2.68 times 10 to the 12th and that distance, I can solve for eccentricity, divide by a, really subtract 1, divide by -1, and you get an eccentricity of 0.97. So this is a very eccentric orbit. It is a very, very flat, long ellipse. Once I calculate the eccentricity, I can actually just plug it back into this equation and find the aphelion distance, 5.27 times 10 to the 12th meters. That's kind of getting to be out where Pluto is at. So that's kind of a quick overview of Kepler's laws and a few things we can do with them. What we'll look at in the next lesson is looking at energy of orbits and how we can use energy to also describe what's happening in an orbit.